and welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to discuss hash pointers, as well as a few blockchain-related data structures that will allow us to generate a simple blockchain. So the first thing that we need to discuss is what is a hash pointer. If you've done programming in C or Rust or Java, you're probably familiar with the concept of pointers or object references. They're just a pointer to some location in data that stores an object. A hash pointer adds an additional piece of data to this, namely a cryptographic hash of that data or some other or some representation of that object or data located there. So why do we add this? So you'll recall from the previous lecture that a hash can give you a finite fixed size representation of the data that you run through the hash function. So what this means is that just like a regular pointer, we can point to where the data is, but by adding a hash to that pointer to create a hash pointer, we can allow people to verify that that data has not been modified. If it is modified, if you've created the hash pointer, you'll know this because you'll get a different hash value when you run the data through the hash function. So here we can see a graphical representation of a hash pointer to a string. This specific string is, in all caps, "This class is great," as I'm sure you'll all agree. The SHA-256 hash of that value is included in the hash pointer. So not only does the pointer point to where this string is located in memory, it also includes that hash ECFBB ... And if I later go to look and see what is located in this piece of memory, and I see, all right, it is "this class is great," and the hash of "this class is great" equals the hash in the hash pointer, I can tell that this data has not been modified since the time that I created the hash pointer. So all is well if it still says "this class is great." Now, let's assume somebody tries to maliciously modify the data. It actually doesn't have to be malicious. There could be some other issue like data corruption, or somebody inadvertently changed it. So our hash pointer still has the same hash value, that ECFBB ... However, note that our string, instead of saying "this class is good," now says "this class is bad," an obvious untruth. If we try to run the SHA-256 hash function of "this class is bad," you'll note that we get FA86 ... This does not equal the hash value that we got earlier and is stored in the hash pointer. Therefore, we know that this data has been modified at some point since the creation of this pointer. So now that we understand what a hash pointer is, we actually can use a lot of the basic data structures used in computer science, modify them with hash pointers instead of traditional pointers, and we now have tamper-resistant versions of these naive data structures. So think of any data structure that uses pointers: linked lists, binary trees. If we just change these pointers to hash pointers, we now have tamper-resistant versions of them. It's very simple. One of the first data structures that you probably learned if you took a data structures class was a linked list. This is simply a list where each individual node or element of data points to another node all the way until null, indicating the end of the list. If we replace those pointers with hash pointers, we now have a basic blockchain. So here we can look at the head hash pointer, which points to the head of the linked list. I see that there is data 3 stored there. There is a hash pointer pointing back to the node storing data 2. From there, a hash pointer pointing back to the node storing data 1. And before that, it points to null, indicating the end of the list. Canonically, we will often look at blockchains as sort of a reversed linked list, where we'll start at data 1 and go to data 2 and then to data 3, because that's the way they're generated. However, from a data structures perspective, this is the same as a linked list. You can just think we are constantly adding data onto the head of the linked list. Again, the only difference between a naive basic blockchain and a simple linked list is just that we've replaced the pointers with hash pointers. So why is this tamper resistant? Well, recall that the hash pointer is taking the hash of all the data in the previous node that it points to. This also includes, this data in this previous node, the hash of that previous node. So if we think of what data is stored in that first node on this slide, it includes both the hash of null as well as data 1. In the second node, the data consisting in that node is both the hash of data 1 as well as data 2. So if at any point we try to modify data, this will be propagated all the way up to the head of the linked list, all the way up through the blockchain. So in this example, I have strike through fake data, right? So somebody tried to modify this first node, this first block in the blockchain. But what's going to happen here? In the second node, the hash pointer is no longer going to be valid. The result that it gives you for fake data is going to be different than data 1. Since that hash will be different, the hash for the third node will be different because it's taking the hash of all the data, which includes both the previous hash and data 2, in the second node, etc. And this will propagate all the way up. So it becomes very easy to tell if at any point in the blockchain some data was modified, because hashes will be modified all the way up through. For a valid blockchain, the hashes will be modified and propagated all the way up to the head, which means that if we'd like to see if a blockchain has been modified, we can just check to see, does our head pointer hash equal what we expect it to be? We don't actually have to go through and check every single hash, since any invalid hashes will propagate all the way to the end of the blockchain. We can also modify other data structures to create more tamper resistance versions of them. For example, a binary tree. If we replace the pointers in a binary tree with hash pointers, and we only store data at the leaves, at the edges of this, we now have something called a Merkle tree. A Merkle tree is used quite often in blockchain technologies. It's simply a binary tree that is a tree that can have 2 nodes and data at each level, or data. No data is stored in the interior nodes, only in the leaf nodes. If you take the hash of this entire tree, that is what's called the Merkle Root. So here, let's walk through an example of some data in a Merkle tree. So I have a hash function, which in this case is only going to return a 256, a simple 256-bit hash value. So let's say my data at the nodes hashes to F7, 18, 76, and 4B. All of these are hexadecimal values. I now can make a tree out of this. And so F7 and 18, those 2 nodes, I will take their hash values, concatenate them together, and hash that to get 5A. For 76 and 4B, I take the hash values for those 2 nodes, I concatenate them together, and I get the hash value 99. I continue propagating up the tree until I get to the Merkle root, which has 8C. So now, just like with a linked list, if any data has been modified anywhere in this tree, I can simply look at the Merkle root and determine whether or not data has been modified or not. I can make sure that the Merkle tree is valid. So why do we want to do this and not simply use that naive blockchain, that simple linked list with hash pointers instead of traditional pointers? Well, Merkle trees, because they are binary search trees, are going to allow you to do a couple of different interesting things. So first, we can actually prove that something is a member, a specific item is a member of a Merkle tree in log n time. So just like traversing a traditional binary search tree, which you can find something or determine if it doesn't exist in log n time, we can do that with a Merkle tree. So we can determine, for instance, if a transaction occurred or not in a particular block. If we have a sorted Merkle tree, we can disprove membership, because we'll know if something exists or not based on whether or not those nodes exist or not. So why would we use Merkle trees? Again, good access time. Traversing a tree is much simpler than traversing a linked list, which is, to find anything, you've really got O of n traversal time. Just like with a naive blockchain, we can simply store the Merkle root and verify the entire tree. Finally, we can verify that a particular piece of data is stored in a Merkle tree in O log n time. Or if the Merkle tree has been sorted, we can verify non-membership. That is, something does not exist in this particular Merkle tree. In Bitcoin and many other blockchain technologies, Merkle trees are used in a few different places. If you've ever looked at a Bitcoin block explorer, you may see something called the Merkle root. So this is the Merkle root of the Merkle tree for all transactions included in that block. That allows a Bitcoin node to verify that the list of transactions is valid and what is expected to be in this block. Another benefit, and we'll get more into detail on this when we talk about mining, is that it allows mining to be approximately equally difficult no matter how many transactions are included. If it were more difficult to add more transactions to a block, what you might see is that miners would be incentivized to only generate blocks that have a small number or perhaps no transactions. This would really go against what Bitcoin is trying to do, to generate a peer-to-peer electronic cash system. If miners do nothing but mine, but they don't include any transactions, this isn't really going to allow people to use Bitcoin on a day-to-day basis. However, since once a mining node, a miner has put together this Merkle tree, they can simply use the Merkle root, which again is of a fixed size. And so it doesn't matter if you have 0 elements in your Merkle tree or if you have 100 transactions in your Merkle tree. Either way, in terms of doing the computations for mining, you're only dealing with the same size of data, this Merkle root. So this means, since you do get often transaction cost, you will get money. Basically, you will get Bitcoin, and for including transactions, we're going to incentivize miners to include transactions here. They're not going to lose anything by not including a transaction. So this is from a recent Bitcoin block, number 540822. I just wanted to show, since we've discussed a lot of what these values are and what they mean, let's take a look at an actual Bitcoin block. So here we can see that there were 3,193 transactions included here, moving approximately, and this is estimated, and we'll talk about why it's estimated a little bit later, 789 Bitcoin from one address to another. In transaction fees, that is how much it costs for all these transactions to take place, was 15/100ths of a Bitcoin. We can see the hash of it, that is, what is the hash of this entire block. And you'll notice that this is a very, very small number. There are a lot of zeros in front of it. And that's going to come in handy when we talk about proof of work and mining. So do note that the hash of this block, the hash of the previous block, and the hash of the next block all have a lot of zeros at the front, which means that they are, in the big scheme of things, relatively small values. This will come in handy, as I said, in the near future. It's not just a coincidence that all of these hashes are so small. Finally, we can see the Merkle root of all of the transactions stored in here. So transactions in Bitcoin are stored in a Merkle tree, but the Merkle root is included as a way of verifying which transactions have taken place in that particular block. So hash pointers seem like a really interesting, cool, and useful addition to our arsenal for data structures. And they are absolutely integral to building blockchain and related data structures. However, there are a few places where hash pointers cannot be used. So first is in any data structure that doesn't have explicit pointers. We could protect these in other ways, but just using a hash pointer, we can't create pointers to different elements in an array, for instance, since those are all simply offset from an initial point. You cannot use a hash pointer in any place that a data structure has cycles. That is, data structures must be acyclic. If there is a cycle in the data structure, so something like a graph, a cyclic graph, then there's no starting point for hashes. They all have to depend upon each other. There needs to be some specific starting point. So trees that have a root, linked lists which have a head, all of these have some starting point for hashes. If you have some sort of data structure that doesn't have any starting point, that's simply, for example, like an undirected graph that has cycles in it, there's no place to start. There's no place to have your initial hash. And so hash pointers simply won't work. So now that we understand the basic data structures of blockchain and the use of hashes and hash pointers, in the next lecture, we'll discuss a little bit more about how hashes work internally, and we'll actually generate a simple blockchain amongst multiple members of a network.